So this video is going to focus on precipitation reactions, which generally follow a set equation where you have two ionic solutions that are mixed together. And when they are mixed together, one of the pairs of ions is able to form a precipitate, an insoluble solid that is going to separate from the remaining ions in solution. You've probably heard of these before, referred to as double replacement reactions. And we do not actually have to perform these reactions to determine if a precipitate has formed. We can use our solubility rules to determine this. So if a substance is going to be able to dissolve and form a solution, both the solute and the solvent have to spread out, and they require energy for that to happen. That's the delta H that you're seeing there. If the amount of energy they require to spread out is more than the amount of energy that is released when they mix together and form their solution, then you have a precipitate form, because you are not going to have a reaction take energy, require more energy than it's able to release to generate a solution spontaneously. So these solubility rules are ones that you need to be familiar with. You will notice that the majority of these solubility rules focus on your nonmetals or your polyatomic anions. There are way too many metals to begin to try to describe every metal's solubility, so this makes it a little bit more reasonable to examine. You will notice on the top 4 rows that the compounds that contain the ions that are listed are soluble. Any compound that contains an alkali metal or ammonium will always dissolve, will always generate more energy than it requires to separate and to form that solution. We also see that happen with our chlorates. That could be a perchlorate or a chlorate. Our chlorites, chlorite or hypochlorite. Our acetates, as well as our nitrates and nitrites. But when we get into the chlorides and the bromides and the iodides, we see that there are 3 metals that when chloride, bromide, or iodide is paired with, are not capable of remaining in solution, and they would form precipitates. Those that combine with lead 2, silver, or mercury 1. With sulfates, the majority are going to be soluble as well, but there are a few more exceptions than we saw in the previous example. Lead 2, strontium, barium, mercury 1, mercury 2, silver, and calcium should all form precipitates in the presence of sulfate ions. Our hydroxides, our carbonates, our phosphates, our chromates, our sulfides, our oxalates, and our sulfides are primarily insoluble. The exceptions are going to be the same that you saw previously, your alkali metals and ammonium. I do want you to notice with hydroxide that although it doesn't form a precipitate, it does make a gas, and we'll talk about that with our gas-producing reactions. But hydroxides also aren't going to readily form precipitates if they are paired with calcium, barium, or strontium. If there is enough of either ion present, they will form precipitates, but they do have the ability to dissolve and form dilute solutions of those compounds. With your carbonates, your phosphates, your chromates, your sulfides, and oxalates, the only exceptions are your alkali metals and ammonium. But with sulfides, you can bring in your group 2 alkaline earth metals as well with the alkali metals and ammonium to generate compounds that are soluble. But again, for the latter part of this chart, those are compounds that are primarily going to be insoluble, that are going to make precipitates. So we can use our chart to determine whether each of these compounds are going to be soluble or insoluble in solution. If they are soluble, we are to determine what ions they would generate. So if I look at my rule for sulfate, and this is going to be the only one I can go back on, after this you're going to want to look at your solubility rules. You will notice that sulfates are soluble, except when they're paired with one of those metals, lead, strontium, barium, mercury, silver, or calcium. And iron does not happen to be one of those particular metals. So that would be a compound that is soluble. And if I was going to split it into its respective ions, because sulfate is -2, the iron, since it's a 1-to-1 ratio, would have had to be +2. In our next example, AgCl, the solubility rule for chlorides is that they are all soluble unless they're paired with lead 2, silver, or mercury 1. Because chloride is paired with silver in this compound, it would be insoluble, and silver chloride would have formed a precipitate rather than dissolving in water. The next compound, aluminum sulfide, if you look at your sulfides rule, I believe you're going to see that they are insoluble unless they are paired with an alkali metal, ammonium, or one of your group 2 alkaline earth metals, and aluminum is not one of those. So because of that, if aluminum and sulfur ions were placed near one another in a mixture, a precipitate would form. With BaOH2, the hydroxides are also primarily insoluble, but they will be soluble if you have them with an alkali metal, and they will be slightly soluble with barium, calcium, and strontium. So they have the ability to dissolve. So this would be a soluble compound, and when it's split into its ions, you would have the barium ion, which has a charge of +2, and you would have hydroxide, which has a charge of -1. In our final example, you can actually look at both ions because sodium is an alkali metal, and by definition, alkali metals are always going to be soluble in aqueous solution. If you did look at phosphate, you would see that they are primarily insoluble, with the exception being ammonium and your alkali metals. So either way you look at that particular compound, it would be soluble, it would dissolve in water, and when it splits into its respective ions, you would have sodium ions and phosphate ions, sodium being +1 and phosphate being -3. So these last few examples are going to be to determine when you mix two solutions together, what forms, what happens? Do you get something that is no longer transparent, that is cloudy, aka a precipitate? Or do you just have a physical change occur where the ions are just mixed together in a container? So I want to look at the ions that can make up nickel 2 chlorate and sodium carbonate. I know nickel is 2+ because chlorate was -1, and I have 2 of them. And I know that sodium is always +1 and carbonate is always -2. So if I want to see if the new compounds are going to form something insoluble, I want to switch up the cations and pair them with new anions. So I'm going to put sodium and chlorate together, and when I do that, I make NaClO3. If you look at your solubility rules for chlorates, or if you look at them for alkali metals, you see that they're always soluble, so that did not form a precipitate. If I look at the other two, nickel and carbonate, I would see that they're both +2 and -2. That would leave me with a formula of NiCO3. But that carbonates are primarily insoluble, and nickel is not one of the exceptions. So a precipitate would form when you mix these two compounds together. The two ions making up nickel carbonate, Ni2+ and CO3 2, would make the precipitate of NiCO3. If I move on to my next example, again, these are all aqueous compounds. I know they're soluble. You can check your solubility rules out, but these are all soluble to begin with. So sulfates -2, Fe would need to be +2. And with potassium sulfide, potassium's always +1, sulfur would be -2. I want to pair the cations with new partners. So Fe is going to go off with S. They're both +2 and -2 respectively, making FeS. While K+ is going to go off with SO4 2. Sorry, I forgot that I had to do the other part first. I'll hush. With FeS, if you look at your rule for sulfides, you will see that Fe is not one of the exceptions. So that did not generate a soluble substance. This would be your precipitate. But we do want to check out K and SO4 because you could have more than one precipitate form when you mix two aqueous solutions together. I don't think that's going to be the case because K+ and SO4 2 would make K2SO4. You have an alkali metal, which is always soluble, and sulfates are going to be soluble in the presence of potassium. So the two ions that were used to make your precipitate, Fe2+ and S2-, were combined together to form the precipitate of FeS. In our final two examples, we have NaOH and Li3PO4. NaOH splits into its cation and anion, sodium plus and OH minus. Lithium phosphate would also produce ions in aqueous solution, lithium plus 1 and phosphate minus 3. Sodium and lithium switch partners. Sodium goes off with phosphate, lithium goes off with hydroxide, making Na3PO4. It's an alkali metal, so it's always going to be soluble, even if it's paired with a super insoluble anion, phosphate. And lithium's going to go off with hydroxide, and we see that when that forms, you have an alkali metal with a hydroxide, so that too would be soluble. In this particular scenario, because you started with two alkali metals, you have no chance of forming a precipitate, and so you don't have an equation to write. There was no precipitate that formed. Sorry, I skipped ahead. I didn't know if I was going to include anything about whether a precipitate didn't form in C. In letter D, you have mercury 1 nitrate and calcium chloride. So if I split those two compounds apart, those would be their respective ions. Mercury is going to go and try to form a precipitate with chlorine. Calcium is going to go and try to form a precipitate with nitrate. When I put mercury 1 with chloride, I see that I have Hg2Cl2. When I put calcium with nitrate, I have Ca with NO32. And I'm sorry I keep jumping ahead. Chlorides are soluble unless they're paired with lead-2, silver, or mercury 1. Mercury 1 would be one of those exceptions, so that is why you had a precipitate form. With calcium nitrate, all nitrates are always soluble, so no precipitate form between that new pairing. So when I write my equation, I would just show the two ions that were used to form the precipitate of mercury 1 chloride, Hg2, 2 plus. I want you to notice I have two chlorines written there because in the chemical precipitate of mercury 1 chloride, I have two chlorines making up that balanced compound. So I need to make sure that my ion charges and the amounts of ions I have make both sides of the equation neutral.